Okay, we went from doing more conversions. I hope you've been practicing doing conversions. It's going to be a big part of the rest of the semester. One thing we need to talk about is density and specific gravity. So we talked about density, it's mass over volume. So we can look at density is equal to mass over volume. We can rearrange that equation. So if we know the density and the volume, we can figure out the mass. It's density times volume. If we know the volume and the density, if we know the mass and the density, you can figure out the volume. The volume is equal to the mass divided by the density. So, knowing the density and one of the other properties, either the mass or the volume, we can do conversions. So here's a case where we calculate the mass in grams of 15 mils of saline solution that has a density of 1.05 grams per mil. Again, when we do conversions, we start off with what we know. Well, we know the density. And we know how much we're starting with. We're starting off with 15, calibrate it, 15 milliliters of solution. We want to figure out the mass in grams. So we're going to multiply that by some factor, grams per mil, which happens to be density. So if the milliliters cancel, well, the density is 1.05 grams per mil. So you have 1.05 times 15. All right, if you do this in our calculator, we get 15.75. Using our rules of significant figures, how many significant figures do we need in the answer? From the problem. 15.0 has how many significant figures? 2. 3. 1.05 has 3. So our answer has to have 3. So what would it be? 15.8. Okay? Pretty straightforward. Well, how do we relate density and specific gravity? Specific gravity is the quantity that compares the density of a substance with the density of water at the same temperature. So here we have specific gravity is equal to density over density. So here the units are the same. So if the units are the same, when you divide them, the units cancel. So specific gravity does not have a unit. Remember what I said, a measurement needs a number and a unit? Well, not for specific gravity. Turns out the density of water, for all practical purposes, is 1 gram per milliliter. So to figure out the specific gravity, you take the density of a substance and divide it by 1. So therefore, the specific gravity of substance is equal to the density, but it doesn't have units. In the previous problem, the density is 1.05 grams per milliliter. Its specific gravity would be 1.05. Now, where do you encounter specific gravity in the health field? A lot of times you get it in urine samples. You get your test back and will have specific gravity. And there's a normal range. If you're outside that range due to excess protein or excess sugar, it could be indicative of diabetes or some other condition, which is why they always, every time you go for a physical, they make you fill out that little cup. So if you're given specific gravity, went down instead of up, and that is okay, chapter 2. We still haven't gotten into chemistry yet. We've just talked about conversions and problem solving. Now we're going to start looking at the basics of chemistry, which means understanding the atom and how it works, and the periodic table. So an element, which we talked about, is a pure substance that cannot be broken down into simpler substances by a chemical reaction. So we have a whole table of them. Each element is identified by a 1 or 2 letter symbol. So elements are arranged in what we call the periodic table, which in your book is at the end of the book. So you have a periodic table. And they call it periodic table because the elements are arranged in periods. The position of an element in a periodic table tells us a lot about its chemical properties. So if you have a periodic table, you can tell a lot about the chemistry of those elements. All right, be that way. Here are some common elements and their symbols. If it's a 2-letter symbol, the first letter is always capitalized. The second letter is always lowercase. 1-letter symbol, it's always capitalized. So you probably know a lot of these. Bromine's Br, carbon is C, chlorine is Cl. Copper is Cu. Most people would intuitively say that because the elements are somewhere based on Latin names, German names, other names. So copper is from cuprum. You notice sodium is Na, natrium. Potassium is K, calcium. So these are just some common ones. Looking at the periodic table from your book, let me point out some other ones that you may know. Fe. Anybody know Fe? What? Iron. Okay. Women's vitamins have iron in them. Men's vitamins don't, because women need to supplement their iron. So if you're a man, you don't want to take a woman's vitamins, you can actually poison yourself by getting too much iron. And a lot of times women that have iron deficiency, they take a product called Slow Fe. Gets the iron into your system slower because if it gets in fast, sometimes women experience nausea and that. Okay. Women's favorites. Here we go. Ag. Silver. Au. Gold. Oh yeah, you guys got that one down. PT. Silver, gold, platinum. Okay. W. Tungsten. Yeah, you know it, or you're reading it out the book? You're reading it out the book. Okay. W is German for Wolfram. All right. PB. Don't look at. Lead. Comes from Latin plumbum. Think of an occupation. It sounds like plumbum. Plumber. That's where they got the name from, because in the old days they put the pipes together with lead, so they're called leaders or plumbers. AS. Arsenic. SI. Here's what I always have fun with. SI. Silicon. Silicone is something completely different. She's in weather stripping. What were you thinking of? Okay. If we look at the periodic table, you can see this one's colored, and the one in your book is colored. We have a little stair step starting at boron. You can see this heavy line and going down this little stair step. That essentially divides the elements. So anything from that stair step to the left are metals. From the stair step to the right are nonmetals. Those that border the stair step, boron, silicon, the ones that are in that yellow-orange, are called metalloids. They're sort of in between metals and nonmetals. So right away, if I asked you titanium, you would say, is it a metal or non-metal? Metal. You probably don't need to know the periodic table to figure out titanium is a metal. But if I said potassium, it's a metal. It's on this side of the table. Sulfur, non-metal. So right away, see, now you know all the elements, whether they're metals or non-metals.
Number one, that's what that goes together.
It goes in with the non-metals. They put hydrogen over here for a reason. But hydrogen goes in with the non-metals. So metals, like we said, are located on the left side of the periodic table. They usually exist as shiny solids. Think of it: gold, platinum, silver. Iron can be shiny. Good conductors of heat and electricity. That's why we have copper wiring, aluminum wiring, metal pans. They're solids at room temperature except for mercury, which is a liquid. Come on, move down. Metalloids are located on a solid line that starts at boron and angles down towards astatine. So there's 7 of them, and these are the ones. They have properties that are intermediate between metals and nonmetals. Okay? Boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. If we look at the human body, 4 nonmetals, oxygen, carbon, hydrogen, and nitrogen, make up 96% of the mass of the human body. They're called the building block elements. So all your proteins, your carbohydrates, your lipids, DNA, mostly composed of those 4 elements. Your major minerals, your potassium, sodium, chlorine, are present in body fluids. Magnesium and sulfur are present in proteins. Calcium and phosphorus, teeth and bones. Take calcium supplements. Then you have trace elements. Arsenic. Yes, you have arsenic in your body. Boron, chromium, cobalt, copper, fluorine, iodine, iron, manganese, molybdenum, nickel, selenium, silicon, zinc. Each of those is present at less than 0.1%. I would have thought that iron would have been there much higher since it's a component of your blood, but apparently it's only less than 0.1%. So compounds, we said, are a pure substance formed by combining two or more elements. We can use what's called a chemical formula, you all know. Shows the elements and it shows the proportions in which they combine. Water, H2O tells me I have 2 hydrogens, 1 oxygen. Propane tells me I have C3H8, I have 3 carbons, 8 hydrogens. Now it tells me how many of each element I have, but it doesn't necessarily tell me how they're put together. So we have to learn how they're put together. The subscripts tell me how much of each we have. So we can draw compounds in many ways. We have the formula, H2O. We have what's called a ball and stick representation. For those of you, or I don't know if there's anybody in this room old enough to remember Tinker Toys, that's what Tinker Toys look like, ball and stick. And we can have what's called space-filling molecules. The space-filling look like a bunch of balls stuck together. That's what the atom would look like. And they just attach to each other. There's no real bond between them. And chemists use different colors. Carbon's usually black, hydrogen is white, oxygen's red, and so forth. They put together their models. So somebody can look at it and say, oh, this is carbon, this is hydrogen, this is oxygen. This is bromine and iodine. Iodine in the solid form is actually purple. And if you go to the drugstore and get tincture of iodine, which is iodine dissolved in ethanol, it's a purple color. Come on. Okay. So, all matter is composed of atoms. Atoms, in turn, are composed of subatomic particles. We're just going to talk about the 3 main ones. We're not going to go into quarks and mesons and gluons. We have a proton has a charge of +1. Its mass is 1.6726 times 10 to the minus 24th grams. Its mass in terms of atomic mass units, that's what AMU stands for, atomic mass units, is 1. A neutron doesn't have a charge. It's neutral. It's slightly heavier than a proton, but its atomic mass unit is 1. Electron has a -1 charge, very small mass, times 10 to the minus 28, so its AMU mass is negligible. What does that mean? When we figure out the mass weight of a compound, we don't usually include the electrons. It's like if you went into a grocery store and you're buying watermelons. So you start sticking watermelons on a scale, obviously it's a big scale. So you have like 10 watermelons on there, and may weigh 50 pounds. So you have a scale that weighs 50 pounds. And you say, hey, while I'm here, I'm going to get some raisins. So you take a handful of raisins and toss them on the scale. You're not going to see that needle move any. So the raisins would represent the electrons. The watermelons would be the protons and neutrons. Okay? So remember, proton +1 charge. Okay? So if a proton walks into the bar, says, I'd like a drink. The bartender says, are you sure? He says, yeah, I'm positive. All right. Neutron walks into a bar, has a drink, and asks the bartender, how much? He says, for you, no charge. Oh, okay, yes, I'm here all week. Thank you. Okay. So if we look at the structure of an atom, we have the nucleus, the core. That's where the protons and neutrons are located. So the nucleus has a positive charge. It's surrounded by electrons. So the electrons have what is called electron cloud around the nucleus. We're not going to go to all the Schrodinger wave equation theories, but the electrons form a cloud around the nucleus. Not an orbit. It's not like the thing in the Big Bang Theory where they show they go around. They actually, it's a probability of being in a circuit space around the nucleus. So most of the weight comes from the nucleus, most of the volume comes from the electron cloud. So if you were in a football stadium, you could think of the electron cloud as the seats around the stadium. The nucleus would be the size of a grape on the 50-yard line. So a lot of an atom is empty space.
The weight belonging to the nucleus and what was in the electrons?
The weight is in the nucleus. The volume is in the electrons. So if we look at the periodic table, there's a symbol. If you look at yours. If you look at lithium, on the top is a whole number. Lithium is 3. That is the atomic number. Symbol is Z. That's the number of protons in the nucleus. So if you look at the periodic table, you see hydrogen is 1, helium is 2, lithium is 3, beryllium is 4, all the way up to, in this case, we have 116. That tells you how many protons. That defines the element. You change the number of protons, you change the element. Okay? Different elements have different atomic numbers. So a neutral atom, atoms are neutral, has no net charge. So if I have 1 proton and the total has to be 0, how many electrons do I have to have for it to be 0? If I have 1 positive, how many negatives do I need? 1. If I have 2 protons, how many electrons do I need? 2. So the number of protons always has to equal the number of electrons in a neutral atom. So if I have sodium has 11 protons, how many electrons? 11. So that's simple. Here. Oh, it's right there. Okay. So here we're looking at the mass number. If you look at the mass number in the periodic table, if we look at hydrogen, it's the one that's 1.008. And there's a reason it's not a whole number. We'll talk about that in a minute. But they round off the mass number here to 1. So if the atomic number is 1, that's 1 proton. How many electrons? 1. How many neutrons? Well, the mass number, down here, the mass number, A is equal to the protons, Z, plus the neutrons. So if the mass number is 1 for hydrogen, Z is 1 proton, how many neutrons has to be?
3.
No. 0. 0 neutrons. 0 plus 1 is 1. If we look at, let's go up to nitrogen, the atomic number is 7. Or rather, the mass number mass number is 14. A is 14. The atomic number is 7. So how many neutrons do I have to have? 7. So to determine the neutrons, you take the mass number and subtract the atomic number. Number of neutrons would equal A minus Z. What about isotopes? What's an isotope? You notice that, for example, chlorine, its mass number in the periodic table is 35.45. Well, it turns out it's a combination of isotopes. We have chlorine 35, atomic number 17. So how many neutrons?
17 minus 35.
35 minus 17 is, you could read it right off here, 18. We have chlorine 37, a different isotope. Notice the atomic numbers are the same. They have to be the same for it to be chlorine. 37 minus 17 is 20. So here we have some chlorine that weighs 35, and some chlorine that weighs 37. Well, chlorine in nature weighs 35.45. It's a combination of the two. Not 50-50, it's a weighted average. I think it's like 80% chlorine 35, 20% chlorine 37. If you look on a periodic table, pretty much none of them have whole number masses. Oxygen is 16, fluorine is 19. But if you look at iron, 55.85, because it's a combination of different isotopes. Hydrogen has 3 isotopes. Hydrogen 1, hydrogen with a neutron, which would be deuterium, and hydrogen with 2 neutrons, which is tritium, which is radioactive. So the atomic weight is the weighted average of all the naturally occurring isotopes. So if you look at lead, atomic number 82, its atomic weight and atomic mass units is 207.2. So it's a combination of the different isotopes. So if you're in the health field, if you go into radiography, or if you happen to be a nurse working anywhere around patients that are receiving radiation, they'll talk about getting tritium treatments, iodine, 131. That means you're talking about a specific isotope of that element, which is radioactive. We're not going to go into all the calculations of how to do that. So some definitions about the periodic table. A row, it's horizontal, is called a period. Hence the name periodic table. A column, up and down, is called a group. We have what are called the main group elements. So if you look on your table, that would be columns 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. There's 6 columns. Those are the main groups. Those columns that have a B in them, 3B through 2B, are the transition elements. If you go down to the bottom, there's those 2 rows, 6 and 7. Those are the inner transition elements. If you look at row 6, you see 57, lanthanum. And there's that little space there. The next one is 72. What comes between 57 and 72? That's row 6 at the bottom, 56 to 71. Those are called the lanthanides. In row 7, you see actinium, 89, and there's that little space there. And then you have thorium to lawrencium, 90 to 103, which fits in there. A couple reasons why they move those to the bottom. One, because if they put them in, it tends to make the periodic table too wide to fit on a piece of paper. So just for aesthetics sake, they took them out. And later on, when we get into electron configuration, you find that by having them down there, it makes the table a lot easier to read. It gives you more information. So again, the ones in blue are the main group. They follow all the rules that we're going to talk about. Transition, not so much. And then the inner transition. They fit into these little gaps here. So let's talk about some specific groups. Group 1A. They have a name, common name, called the alkali metals. Soft and shiny metals, low melting points. You can take metallic sodium and cut it with a spoon. You know, if this was a lab course, I would take some out, show it to you, and cut it with a spoon. It's that soft. And it's very reactive. If you throw it in water, it tends to explode. Which makes a nice demo, which I can't do in here. Column 2, alkaline earth metals. Good conductors of heat and electricity. React with water to form basic solutions. Okay, so what's column 2? A. 7A. Those are the halogens. They exist as two atoms joined together, what we call diatomic. Talk about diatomic elements. Basically, talking about fluorine, bromine, and iodine. Oops, my little thing's not working here. But they all exist as F2, Cl2, Br2, I2. They don't exist individual atoms. They exist like that, called diatomic. There's 3 others: hydrogen, oxygen, and nitrogen. Column 8A are the noble gases. Very stable. Very hard to get them to react. You can, but it takes extraordinary conditions. They're happy just like the way they are. Helium, neon, argon, krypton, xenon, radon. Carbon has 3 elemental forms. It can go in a 3-dimensional network, bond to itself, give us diamond. More of a 2-dimensional network, parallel sheets, which are graphite, which is in your pencil. And it can have this soccer ball configuration, which is called Buckminster Fullerene. It was named after an architect called Buckminster Fuller. I don't know if you heard about him. If you go to Epcot Center, you know, you have that big geodesic dome. He designed that. He designed homes in that shape. It's a very stable structure. Although if you have a house like that, it's kind of hard to hang a picture. So graphite is used as a lubricant. It's a powdered lubricant. Buy at Home Depot and that. Advantage is it doesn't pick up dirt and that. So if you have a block that's sticking, put powdered graphite in it. If you don't have powdered graphite, just take your number 2 pencil and take your T and rub it on your pencil on your T, and you'll get some graphite on there from your pencil, and you can stick it in there and work on your lock. So, let me... Electronic structure. The chemistry of an element is determined by the number of electrons in an atom. So all the chemistry occurs in the electron cloud. And actually, the outer edge of the electron cloud. Nothing occurs in the nucleus. Surprise, surprise. The regions occupied by electrons are called principal energy levels or shells. We're going to call that N. Let's see if I can do this. I'll insert blank page. I can do that. All right. So I have N, principal energy level. So electrons do not move freely in space. They only have specific energy levels. We're going to call them 1, 2, 3, I'm going to go to 4. What does that mean, principal energy levels? Okay. So here I am, I'm an electron. I'm on the ground level. Someone adds energy. Okay. So I get excited and I get up to the next level. Now I'm on the next level. First, ground level was 1, now I'm 2, higher energy level. All right, I lose my energy, I go to relax back, so I'm going to jump off this chair. I'm not going to jump, hold, but I'm going to jump off. Can I stop halfway down? No. So I got a choice. I can either be up here or on the floor. One of the 2 places. Okay? Those are called quantum levels. Quantum means peace. So I got to be here, either level 1, 2, 3, 4, 5, and 6. That's what we're going to start with. Higher the number, the farther away from the nucleus. The farther away from the nucleus, the higher the energy. Level 2 is higher than level 1. Level 3 is higher than level 2. Oops, got to drag that little thing here. Get over here. The number of electrons in the shell. Shell 1 can only have 2 electrons. Shell 2, because it's farther out, you can think of a ball that's farther out, has much more space in it, can hold 8 electrons. Shell 3 can hold 18, and shell 4 can hold 32. Now I'm stuck here. Okay. I don't know if I can move that back. Each shell can have what's called subshells in it. Okay? They're called S, P, D, and F. Those are for German names which describe the shape of the subshells. So here we have subshells. Each orbital has the same number of subshells as its number. So principal level 1 has how many subshells? 1. Principal level 2 has how many subshells? 2. 3 has 3. And 4 has 4. Okay. The subshells are arranged in energy levels too. So we have S, which is lower in energy than P, which is lower in energy, D, which is lower in energy, F. Okay? So, principal energy level 1 has 1 subshell. What's the lowest energy subshell? S. So this has an S. Principal energy level 2 has how many subshells? 2. What's the lowest energy? S. What's the second lowest? After P. Principal energy level 3 has how many subshells? 3. Lowest energy, S. Next one, D. Next one, D. Okay, 4 has 4 subshells. They are
S, B, D, and F.
good. Never get the cup to work right. All right, F. Now the subshells have orbitals. Okay, this is getting complicated. An orbital is a region of space where the probability of finding an electron is high. Okay, what does that mean? So, you're going to walk into a room. The room is completely empty except for a light bulb in the middle of the ceiling and a moth. So I say, you're going to go into the room. Where are you going to find the moth? By the light bulb. Anybody ever have a moth in their house? You ever see it on the wall? Just hanging out on the wall somewhere? So it's not at the light bulb, it's at the wall. But most of the time, there's a high probability it's going to be flying around the light bulb. It gets tired, it sits on the wall. Same thing with electrons. There's a high probability of finding them in a certain location. And that's what those orbitals define, where they're going to be located. So, if we look at the number of orbitals, subshell S has 1 orbital. So we have 1 here. This one has 1. P has 3. Here we have S has 1. P has 3. D has 5. Here we have S is 1, P 3, D 5, F 7. Each orbital can hold a maximum of 2 electrons. So here we're going to go the electrons. So S has 1 orbital. How many electrons can it hold? 2. So here it can hold 1 orbital, 2 electrons. P has 3 orbitals. How many electrons total can it hold? 6. 2 in each of the orbitals. So this can hold 6. 2, 6, 5 orbitals times 2, 10. 2, 6, 10, and 14. So now we'll look at, can't get the pen to work right, the total electrons. So, principal energy level 1, 1 subshell, S, holds a maximum of 2 electrons. So the total number of electrons in principal energy level 1 is 2. Principal energy level 2, 2 subshells, an S and a P, 1 orbital, 3 orbitals, 2 and 6, for a total of 8. Principal energy level 3, 3 subshells, S can hold 2, P can hold 6, D can hold 10, for a total of 18. Principal energy level 4, S holds 2, P holds 6, D holds 10, F holds 14, for a total of 32. Notice they're the same as what we said in the beginning. So what we're saying is we can look at a principal energy level and break it down even further to locate an electron. It's like, okay, you're going to deliver pizza at NC State. Okay, they're back at school. So you know you're going to state. What else do you need to know? You're just going to wander around campus? You know what? Which means you need to know what? Door. Okay, now you're at the dorm. Now you need to know what? Floor. Now you're on the floor. Now you need to know what? Room. Now you have the room. Now you need to know person who wants it. Okay? So get more and more precise as you're going. That's what this does. And we're going to learn how to get that address for each electron. It's pretty simple, he says. Of course, I say everything's pretty simple. Don't panic. Come on. That little slider thing to work here. Why isn't this working? So here are some of the shapes. I told you this. So an s orbital has a spherical shape. So if you have your nucleus and you think of, let's say, a golf ball around the nucleus, that would be the 1s orbital. That would be the probability of finding a 1s electron would be within that sphere defined by a golf ball. The 2s would be like a softball around a golf ball. Much bigger sphere where you could find a 2s electron. 3s would be like a basketball around there, much bigger area you could find a 3s. 4s would be like a beach ball around the basketball, much bigger area. The p orbital actually has a dumbbell shape. Remember I said there was 3 of them. There's one along the x-axis, the y-axis, and the z-axis. So if I wanted to say the electron's in a p orbital, I know it has to be somewhere within that dumbbell. Okay. We now have to do what's called electron configuration. Don't panic. Okay. That's how the electrons are arranged in an atom. The lowest arrangement is called the ground state. The lowest energy. Everything likes to be the lowest energy, okay? I mean, you come in here in the morning, you guys are all the lowest energy state. Okay? Unless you're drinking supercharged coffee or Red Bull. So, electrons are placed in the lowest energy orbitals beginning with the 1s. Each orbital holds a maximum of 2 electrons. So we said the s can hold 2. The p holds how many? 6, because there's 3 orbitals. The d holds how many? 10, because there's a 5. And the f holds 14. Okay. I'm going to, well, hopefully I can draw it on the screen here. So just like if you're working in an orchard, packing apples. So they bring this big truck full of apples. So here you have boxes on the table. Then here you have boxes up on a higher table. Then you have a box on a higher table. Well, which was the easiest to pack first? The ones on the table. They get full, then you have to move to the next higher one. A little bit more effort, more energy. Those get full, now you got to get up on a step ladder and pack the top boxes. Higher energy. So, given a choice, you're always going to start at the easiest one, the lowest energy first. So I'm going to write a little diagram to show you how this goes, because it doesn't necessarily go in order. Because, of course, that would have been too easy. When it gets higher, it kind of flip-flops. So hopefully I can do it on here. So I can do the 1, S, 2, S, P, 3, S, P, D, 4, S, P, D, F, 5, S, P, D, F, 6, S, P, D, and F. So how do they fill? We start at the 1s. I'm going to draw this little arrow. It goes through the 1s. Is it going to go through the 2s? It keeps going. No, it's going to miss it. If I come back up to the top, go through the 2s. It's going to miss everything if it keeps going. So I come back up to the top, I go through the 2p. 2p goes through the 2p and the 3s. And it misses everything. I have to come back up to the here and go through the 3p. Then I go through the 4s. It misses everything. Now I come back up to the top, go through the 3d, the 4p, the 5s. It misses everything. Now I come up to the 4d, 5p, 6s, 4f, 5d, and 6p. Okay. When you do electron configuration, you're going to follow the arrows. All right? Let's look at a simple one. Here. Well, actually, I'm going to move this bit here. No. that back over here. And insert blank page. All right, let's look at some of these. Let's look at time. Okay. Let's start easy one. Hydrogen. Hydrogen. How many electrons? 1. So, looking at our chart, we have to give it its address. What's its principal energy level going to be? Start at the top. What's its principal energy level? 1. What's its subshell going to be? S. How many electrons are we going to stick in the s orbital? How many we got? 1. So we go up here and make a subscript, a superscript rather, 1. That's hydrogen. Let's look at helium. How many electrons? 2. We have 2 electrons. What's the principal energy level we're going to start with? You always start with the lowest one. 1. Subshell. How many electrons? 2. So the subscript we put 2. All right. Lithium. How many electrons? 3. We're going to start with 1. Subshell. How many electrons? No, can't put 3 in there. S can only hold 2. So I can only put what? 2. All right, the 1s box is full. What do I got to go next? What's the next one? 2. I'm going to go to 2, energy level, subshell, S. How many electrons did I put in there? 1. I only have 1 left. You notice if I add superscripts up, they give you the total number of electrons. 2 and 1 is 3. Let's jump to carbon. How many electrons? 6. I start with 1, subshell, number of electrons, 2. Then I have to go to 2, subshell, S. How many electrons can I put there? 2. What's the next one? I've only used 4. I got 2 more left over. What's the next box? 2s, 2p. You always got to have a principal energy level 2p. How many electrons did I put in there? 2. Now I have 2 left. So the electron configuration for carbon is 1s2, 2s2, 2p2. So that tells me where every electron is. Oh, let's shoot for the moon here. Sulfur, how many electrons? Sulfur?
16.
S. 16. First one. 1s2. Next one. 2s2. Next, 2p. How many can I put in a p? P can hold 6. Do I have 6 left? Yeah. So 2p6. So how many have I used so far? 10. What comes after 2p? 3s. There's no 2. Look at the map. How many can I put in an S? 2. So I've used up 12. 3p. How many go there? 4. I can put in 6, but I only have 4 left. 2 plus 2 plus 6 plus 2 plus 4 is 16. So that's the electron configuration for sulfur. Okay, so you should be able to do electron configuration